I think we can now work on our second speaker, Ramzi Khsib, if I do a good job on your name, is a principal software development engineer at AWS Elemental, where he leads compression and science initiatives. With over 2 decades of expertise in video processing and compression, Ramzi has been recognized with 5 awards for technical engineering Emmys, so that's impressive, for his groundbreaking contribution to the field. And we can welcome him to the stage.
So I always make the joke that I have more Emmys than Brad Pitt. So it's a motivation to be in the video compression space. Cool. So today, welcome everyone. Today we're going to talk about how to take an open source video codec to production broadcast grade. I think I can skip the intro. By now you know my first name and somewhat my last name. I keep the pronunciation of my last name secret till I retire. And I've been doing compression since, what was it? AV1, sorry, was it? Since VHS was the streaming service. And we're not going to talk about AV1 on VHS. We're going to talk about SVT AV1. As you saw, SVT AV1 received recognition in the last IBC. But we need from SVT AV1 to have a valid 10-bit AV1 conformant bit stream. And we need real-time performance. We need compression efficiency of 25% compared to HEVC at a reduced latency. And also, the buffer has to be compliant. No underflows, no overflows. So these are kind of the requirements we have for a broadcast-grade encoder. So the agenda for today is we're going to talk about encoder speed up, how we do that, and then how to apply those techniques into real-time performance. We talk about psychovisual optimization, rate control, buffer conformance, and we'll end up with some recommendation and results. So from AV1, with no secret, is computationally heavy compared to previous generations. So we need some optimization technique. Typically, we use CPU features like SIMD, vectorization, AVX, AVX2, AVX 512. We use threading, pin cores, distribute threads among sockets, et cetera, memory, preload, fetching, zero copy, and all that. This is a very classic, but it's not enough. In the video compression space, we need more. So we move to the algorithmic speed up, where you constrain the tool set. So any mode that is, or any tool that is heavy, you do the trade-off between quality and compression. So modes like OBMC, unfortunately, had to be turned off in the live setting of AV1. And also, there is a technique similar to that, is you do prune searching, early termination, early exit on mode decision. And also, there is another trade-off you can do is around loop filters. So sometimes you choose to have the blocking and turn off the restoration filters. So these are techniques that saves compute. Another powerful technique in the production grade is use a pre-processing technique. So instead of waiting for recon pixels to finish, you use source pixels to predetermined coding mode. So you don't need to, in the coding loop, you don't need to go through all the modes, all the combinations. So you predetermine these modes. And you can also use probabilistic approach. Like in Intra, for instance, out of the 100 modes, you can predetermine statistically which modes are most likely to be used. On the AV1 side, there are a few other techniques you can use. Obviously, the frame level, you can encode so many independent frames in parallel. You can use tiles where a row of superblock are coded independently. Wavefront in intra is another technique. And also you can pipeline across stages. So you can do motion estimation while you do entropy coding, while you do quantization. So these are the theoretical speed up opportunities in AV1. So combining all those techniques, so we can, like SIMD would get you 3x, threading would get you 16x. So you might think, yeah, we're there in terms of real-time performance. And unfortunately, no. Because speed up is always limited by the serial function of your, or like the slowest part of your frame encoding. This is classic, nothing too fancy in here. And so in SVT AV1, the approach was to code as many frames in parallel. So you have a window of 3 seconds worth of frames, and any frame that its reference is ready, you start encoding it within that window of 3 seconds. Cool, right? So you have high concurrency. So let's take this example. This is a GOP 3B. So you can start encoding the two iframes, I0 and I16 in parallel, then P1 and P17 in parallel, then B2 and P5, and etc. So what you end up is so many frames in parallel. And this actually, when you choose a sub-GOP of 16, you get more frames in parallel. And that's what the SVT AV1 has as of today. But this comes at a problem, right? So yes, we have the efficient use of available CPU cores. That's great. But we have high maximum latency. And for sports, this is critical. We have also non-deterministic output. So that is another critical for production grade. We have also rate control performance. So when you have non-deterministic output, you have no guarantee on what's the buffer state. And also, the tile level parallelism is not activated or does not provide the speed up we're looking for. So how did we solve this? So how did we approach this problem? So we started by thinking, first of all, the latency, that's a critical component. We cannot wait 3 seconds for worth of frames. So we need a smaller window. So we created the smaller window of just 4 frames. And we created this idea of completion. So completion means for us is frames are considered completed if they are fully encoded, rate control state is updated, and buffer model is updated. So at each instant, we have a crystal clear vision on what's happening in the buffer, and the rate control has full vision of that. So in other words, or as to illustrate this, we create 4 states, starting in progress, ineligible, and completed. We start I0, and those frames in orange are not ready, so we don't encode them. Once I0 is encoded, we start P1, and we have a set of ineligible frames, and then we go with that window of 4 frames. One thing to notice here is a P5. We borrowed this idea from SVT AV1. P5, we don't wait for P5 to finish because there is no reference that at this point needs a P5. So this reduced window looks great, right? It's rate control friendly, low latency, deterministic output. We have strict ordering on frames. Cool, right? We solved the problem, but no. That's engineering. We create another problem, which is this parallelization scaling limitation. What that means is we're encoding less frames in parallel, and we fall back into the problem of Amdahl law, where the serial component is taking over performance. Another term, we need to speed up the serial component. A classic technique in here is we can use a tiling. So tiling, theoretically, if you use 2 tiles, you double your compute. you have two threads separately encoding two sets of superblocks. Cool, right? That's luckily, SBT AV1 have tiling enabled. It produces compliant tiling syntax. But the problem in SBT AV1, the tiles do not provide any gain. So there is no speed up. And why is that? Because when parallel frames are being executed, tiling will act serially. So what that means is, whenever we encode in parallel those frames, we have to stall all those threads and wait for CDEF to finish to unblock those threads. So as you can see from this graph, we have a lot of waiting time, waiting for serial CDEF to happen. And then we can continue with the execution. So there is really a diminished return from using tiling in this case. Again, how do we solve this? So the approach to do this is we noticed that the boundary between the tiles are the bottleneck. So what we did is we broke the superblock into interior and edge sections. And inside the coding loop, instead of stalling the threads, we filter right away the interior section. They don't need any dependency from other tiles. And then after all tiles are completed, we filter the superblock edges, which is smaller compared to filtering the entire superblock boundaries. So that's how we made the style-aware multi-threaded filters. And the same solution, we applied it to CDEF. It follows the same idea, right? Cool. Now, we turned out this was kind of enough. Well, it kept us on the margin. So what we did is we approached the problem again from another perspective. So we did the presets retuning. So we used constraint multi-objective optimization for a better trade-off between quality, subjective and objective, and compute. And since we're talking about quality, we spend a lot of time into psychovisual optimization, or how to make quality look better. So SVT AV1 objective number look great, 15 to 25% versus any open HEVC. That's great, but it comes at a problem again. There is an excessive smoothness and detail loss, and this is a huge problem for broadcast grade content. As an illustration, so in this example, you can tell the grain and the texture is lost even at close to pristine. So this is a real problem, especially if you compare this to HEVC, where at the price tag of 15% more bits and a bit higher VMAP, the texture is retained. The grass is greener in HEVC. So there we use this technique or this preset in AV1 called sharpness increase. Again, we saw some unsatisfactory results, and the biggest problem was the bit rate was higher than HEVC. So again, the visual results were not there. Bit rate is higher, so this is not a solution, right? We cannot use this. So back to the whiteboard. So the idea, we want to retain the same level of texture of HEVC, and we have some challenges. We want to adapt AV1 tools to the HEVC kind of texture preservation. In AV1, we have different quantization mechanics, additional transform, and non-square transform. So we need to adapt those. But the biggest problem we found, and the biggest difference was AQ. And AQ in AV1 is problematic because the maps generated are not fine enough. So what we did is we did approach this into 3 steps. Because we like the HEVC finer grain maps, so we needed to generate an HEVC, or we generated an HEVC-like map. and then adapt that using superblock QPs to AV1. And we use the segments to refine, to kind of transpose those maps to AV1. It kind of worked with some limitation, obviously, because AV1 does not offer higher or finer detail compared to HEVC. Now, let's turn our attention to the rate control. I mentioned this is a critical requirement. In rate control, one of the key components is the green arrow, which is the feedback mechanism. That's when we know where we're at in the buffer. That's when we know if an underflow is about to happen. The green arrow is critical in any rate control system. So back to the example I showed with SVT AV1. Scenes that are being encoded at the same time. You have scene 0, iframe from scene 0, and iframe from scene 1 being encoded at the same time. That's challenging for a rate control perspective because when you start projecting the buffer, you might already be in an underflow because you're still encoding the frames in sequential order until they hit the next scene, and then the underflow is already happening and you cannot recover. So our approach, because we're using smaller window, 4 frames, deterministic output, so we know at each instant how far we are in terms of the buffer, and we can adjust or react faster. Now, I want to conclude my talk with a few recommendations. I think the first one is SVT AV1 did a great job on the joint, frame, row, frame and GOP level. But I think there is more, like I showed in the tile-aware performance. Also, rate control is a key component. And deterministic output is, I cannot emphasize enough how much that is critical, even from testing standpoint. Like, you want to reproduce what happened, and sometimes you cannot have bit exact output. The other recommendation is the perceptual consideration. So releases of SVT AV1 are heavily tuned on objective metrics, but that's great. We show progress. We show that we're moving the needle, but it does not capture the full picture. Like there are artifacts that slip. There are problems like banding, blurriness, sometimes blocking artifacts that the metric in their average skip. So we need a constrained multi-objective optimization where you use multiple metrics instead of one set or 2 metrics. The last, I think, the last recommendation is adaptive quantization. I think this feature, if you talk to any broadcast grade or production ready encoder vendor, this is a critical feature. It always out of the open source because it's a nemesis for objective metric. I think it's about time to marry the two. To finish, I think X264, 65 have a psycho-visual tools like SciRDO, SciRDOQ. I think porting these tools to SVT AV1 is a great. Also merging the SVT AV1 Sci branches that have cool features there. An input filter is worth another discussion. I think there is a lot of compression efficiency in the input filter. Results. So changing to smaller window, we were able to achieve the higher throughput, improved overall quality, and reduced latency. And using a GOP or sub-GOP of 3B, we moved from 42 FPS, which is below real time, to the comfortable 77 frames per second. And visually, now we're able to match the HEVC quality in terms of texture preservation and bitrate saving. So I think, and it's not enough. So we're still working on the quality of AV1. And that concludes my talk.
Right on time.
Yes.
We can
No
have,
latency.
Yeah, we can take one more question from the audience. Marcus?
Yes,
please?
would be interested in, have you done any energy considerations? Because, I mean, there's obviously a lot to gain there as well.
Not really, but I think the very fact that we have limited resources in terms of CPU and all of that, so that's a byproduct of the energy, and I think we always optimize for compute and quality, so it's always a trade-off. So energy is, even if it was not mentioned, is always there. So compute, cost is energy and money. That's, yeah, cool.
Thank you. We can take more questions during the
Sure.
coffee break.